So first up, happy Halloween tomorrow. Yay.
What was the attendance code?
It's in the chat, or you can ask in the
Yes,
chat.
ma'am. Thank you. Sorry.
That's okay. The quiz is going to open today at 11 a.m. and it closes Sunday at noon. So please keep in mind that tomorrow is Halloween. So if you are planning on enjoying Halloween in any way, plan ahead for that. If your enjoyment of Halloween is going to cause you to sleep past Sunday at noon, you should do the quiz today or early morning tomorrow. That's the main point of those two bullets going together. Also, yesterday I sent out an announcement with a ton of information about chapter 18 on Top Hat and also just the rest of the semester and what to expect. So everybody needs to read that announcement. It should answer a lot of questions that you have or just kind of, direct you for the rest of the semester. Okay, today we're going to do problems that are from chapter 18. If you can handle today's problem session, you will have no issues with the quiz. The quiz is pretty straightforward. There are only 3 problems that I think are actually kind of on a challenging level. Everything else should feel pretty simple. A lot of it's very repetitive, and so you'll notice that you actually aren't getting as much time to do this quiz as you have for other quizzes. One of the reasons for that is 1, I don't think you need that much time to do it. 2, I found a bunch of my quiz questions from last time on CHEM. And 3, you're about to take an exam that is going to have more questions at a faster pace. So you need to start being able to think about these things more quickly. Okay, so these are our first 2 problems. Go ahead and write them down. I'm going to put us in the breakout rooms just to kind of treat these as a warm-up. So go ahead and write them down. And I'm going to put you into slightly larger breakout rooms to see if that helps us get a little further with these problems. Okay, so when you have the problems written down, you can go to your breakout rooms. Would you say it's like 100% or like 1% enolate?
100%.
Yeah, there's not another carbon.
There's nothing else there.
Well, yeah, so what I'm really talking about is the strength of the base, right? We're talking about our acid-base equilibrium. Do we favor this as our acid or this as our acid, right? What's the pKa here?
Somewhere around 20.
25.
No.
Like 9 or 10.
36.
Yeah, there we go. So 36. I know a lot of you are typing in the chat, but when I'm teaching on my tablet, it's really difficult for me to have the chat open because it takes up too much space. What's the pK of this one? Just roughly. The pK of an alpha proton to an ester.
1920.
So that's for, yeah, 1920 is more for an aldehyde or a ketone. For an ester, it's going to be higher, around 25.
So that one's the 26-ish one.
Yeah. So which side of this do we favor? Do we favor the products or the reactants?
Products.
The product.
Products, right? So pretty heavily, right? A 10 to 11 difference. So it is mostly enolate. The reason that's important is because in the next step, you're going to add this. And because it's 100% enolate, we're just going to see a big SN2 reaction here. Next chapter, we'll see why it's important that it's 100% enolate here. And we end up just adding an ethyl group. How many of you guys got this?
I did. Yay.
We did.
Yes.
Well, I forgot the double bond was there, but the rest of it I got right.
Cool. Okay, in our next one, I know this one was a little bit trickier, but this is in the notes, at least in the videos that I sent out. So we have sodium hydride, right? Sodium plus, hydride minus. Where have we seen hydride before?
In acids?
No, in acids, that's H plus, right?
Yeah.
Basically, we have the opposite of an acid here. So we've seen hydride act as a nucleophile before, but what else can it act as?
Reducing agent.
Yeah, we've also seen it as part of reducing agents.
A
For those,
base.
you have to have those metals present. So we've seen it as part of reducing agents. What
A
else?
base.
Yes, they can act as a base. So where do we have an acidic proton on this molecule? I'm just going to letter all of these carbons. Do we have anything acidic on this molecule?
On carbon E.
E.
Yeah. Our hydrogen on carbon E is an alpha proton. It's fairly acidic. So we can pull it off using hydride. Okay, and that gives us this guy. What comes next?
The negative charge wants to attack the chlorine, or the carbon attached to the chlorine, so it ends up creating like a cyclo, pentene.
Right, exactly. So basically, we created a nucleophile on the same molecule as a primary alkyl halide. So we're setting up an intramolecular SN2 reaction. This is going to make a cyclic structure, so numbering your carbons real fast can help you draw out the correct structure. So we're going to have a 5-membered ring, and then we have to also remember the nitrile group coming off of it. One of the more common mistakes I see for this type of problem is drawing the 5-membered ring and then drawing the nitrile coming off of it. That's wrong for 2 reasons. 1, because it's missing 1 carbon, and 2, because how dare you draw a 5 bonded carbon, right?
LOL.
So
It's
be really careful. In this chapter and chapter 19 especially, always, always, always count your carbons at the end of a problem. That will save you a lot of pain.
I have a question though.
Sure.
On the last one, so it doesn't matter. Oh my gosh, my computer's falling. It doesn't matter like what, like if it was a different, so say chlorine wasn't like there. Would there have to always be, what I'm trying to say is like, would there always have to be,
There would have to be a leaving group of some sort.
some sort, yeah. So say the leaving group was on, say there was attached to 4, would it still do this, like, would you still know to take it out?
Yeah, I mean, it would still do that, but you would end up with a four-membered ring. And so the closer this gets to the enolate, the
Mhm.
less likely that is to occur. Like by the time it's over here, it would probably react with a separate molecule.
Okay, like it'll be 1, 2.
Yeah, like if it was something like this, it would just react with another molecule of itself and probably end up creating like a polymer.
Okay,
Um,
thank you.
yeah. Okay. So next problem. We're starting off with an aldehyde, and we have LDA. We're going to work together on this one, otherwise we're not even going to come close to finishing these problems. So what does LDA do?
Creates carbanion at the alpha carbon or the alpha
The
hydrogen.
beta.
Right, so it's a base, right? So when you see LDA, I want you to think two things. It's a base and it's bulky, right? In this chapter, having a base means you're going to deprotonate the alpha carbon. In this chapter, if you're doing a problem and you do not deprotonate an alpha carbon, you've already messed up because that's what this chapter is literally about. Okay, we have LDA. I'm just going to write B minus. I don't have enough space to draw out the structure here. And we create our enolate. Okay, so this is after step one. And then we add in our next reagent. What's gonna happen?
You're gonna
Is it
attach
gonna
it where the carbon is, but it's gonna be in the resonance form.
No, nothing about a resonance form. We have a nucleophile.
Nucleophilic attack on the carbonyl carbon.
Yeah.
Right, yeah. So we have a carboxylic acid derivative here, right?
Yes.
So we're going to attack the carbonyl carbon.
And then protonate.
No, we're not gonna protonate.
Oh. Oh, you have to reform it to kick off the leaving group?
Right. So I'm regretting my choice of where I put things right now. I ran out of space. Okay. So we're here. We are going to reform our double bond. What are we going to kick out? Chlorine or ethoxide?
chlorine?
Fluorine.
Chlorine, yeah. It's a much better leaving group
Oh, okay.
because chloride is a weaker base than
It's-
ethoxide.
It's more readily to leave.
Right. So remember, the weaker base is going to be the better leaving group.
Okay.
Okay. And then the last step, water, is just, that's a traditional workup, so it doesn't actually do anything. Okay. So this is your product here. That's all. Okay, any questions about this?
Wait, you said water just doesn't do anything. It's just kind of there.
Yeah, the only way it would do something was if you had H3O plus. If we had H3O plus, what would happen?
Then it would protonate something, right?
And alcohol.
Well, no,
Yeah.
'cause they reform the oxygen, so you protonate.
Would it attack the OET? Because that has a negative.
No?
I mean, they get a carboxylic acid.
Yes, it would hydrolyze the ester. Okay, let's move on to the next one. Okay, so there are two problems here. They both use pretty similar ideas. They both start off with a halogen. We have different conditions and our substrates are very different. So in this first one, we have bromine and acetic acid, and we have a ketone. I'm going to go ahead and give you about a minute to think about this on your own. Would you guys like to go into breakout rooms for this?
Yeah.
No.
Okay, it was
Sure.
very helpful to get two people giving opposing opinions. Okay, how about this? I'm gonna give you guys one more chance at breakout rooms. I'm gonna stop into each one. This is your chance to earn back your attendance credit. I am gonna recreate them because I think some people were pretty unhappy with their breakout rooms. So I'm gonna open them all up now. Just gonna give you about 2 minutes.
Hold on. Whew. All right, bet.
So you can join the breakout room when you have the structures written out.
The
bromine.
and attack the alpha carbon.
Well, so you can't just
Hydrogen of the alpha
attack
carbon.
the alpha carbon. You can't just attack the alpha carbon.
The hydrogen
Does
pisses
the
off.
bromine attack the beta hydrogen?
Well, so it is the alpha hydrogen that we're concerned about, but is bromine a nucleophile or like a base?
No, it's just itself.
No, so we can form an enolate and base, but we are in acidic conditions. What do we form in acidic conditions?
An enol?
An enol, yeah. And an enol is nucleophilic.
Okay.
So what happens when you react an enol with a halogen? Does anybody know?
Add bromine.
It
Right.
makes it
Get a
pull off
strong-
the hydrogen and make a carbanion.
Well, we're not going to make a carbanion because we're an acid. Basically, you make an enol, and then it adds on the bromine, and then it tautomerizes back to the keto form. So we're going through the process of this attacking bromine. And then you deprotonate to get here. In the breakout rooms that I went to, I saw a lot of adding on acetic acid to replace the bromine. Is acetic acid a good nucleophile?
No.
No. Acetate is a good nucleophile. Well, it's a mediocre nucleophile, but it can act as a nucleophile. Acetic acid, though, cannot. Acetic acid is just there to create enough acid to allow the formation of the enol. So this is your product. This is under the alpha halogenation section of the chapter. Okay.
Wait, hold on. So I'm sorry, I don't know who I interrupted, but because that looks like the first step. So the CH3CO2, like that's nothing, or
It's used in the process of creating the enol.
I was gonna ask,
So
is it
it's just a source of H+, that's all.
okay.
Well, that's disturbing.
Okay, the next one is a very specific reaction. Does anybody know what reaction is occurring here?
Is it a halo formation, or would it have to be an excess for it to be one?
Yeah, this is the halo form reaction. So typically when something is written out like this without any indication of equivalence, you can typically assume it's in excess. I usually do the favor of writing out excess for you guys, but that's kind of backwards. Usually if it's just written out, that's assumed to be excess equivalence. If it says one equivalent, then you know it's one equivalent. Yeah, so this is perfectly fine to write out. So if you look at your notes for the halo form reaction, what's going to happen is you continue to deprotonate the only place where there are alpha protons over and over and do a very similar thing that we just did up there. Oops. Until you've replaced all of the alpha hydrogens with iodine. At that point, hydroxide is able to come in and attack. And you kick out CI3. You end up with your carboxylic acid, which is then deprotonated because you're in base. And you also have CI3. So either one of those could do the deprotonating, but then we have H3O plus as our second step, so you get your carboxylic acid back. So we're gonna go from here to here and then back. So minus a proton, plus proton. So again, this is very specifically the halo form reaction. Okay, so we're out of time today. I had a ton more problems written out. So what I'm gonna do is send out the PowerPoint with all the rest of the problems and we'll go over them on Monday. So after your quiz, everybody should spend some time on these problems. I'm gonna put you into breakout rooms again on Monday and basically give you a chance to go over all of the problems together. So you should have the PowerPoint, you should have your notes. I'm gonna give us about like 20 minutes to go over all of those. Well, I'll give you guys 10 to 15 minutes in your breakout rooms. Ann and I will hop around through the breakout rooms. And then it's going to be the class together going over them. And then we'll talk about a couple more things. Monday's class is going to move quickly because we are starting to get just a little bit behind, but not a lot. We're doing fine, especially since I built in a review week at the end of the semester. That's kind of just a buffer zone. So anyway, I'm gonna let you guys go because we are out of time, and I'll see you Monday. Have a happy and safe Halloween. Be very, very safe.
You.
Bye. Have a good one.
Bye. Thank you.
Bye.
Thank you. Have a good one. Hey, Dr. V, I just had a question about that last problem.
Sure.
So the final product is the carboxylic acid, correct?
Mm-hmm.
Okay, and then so the H3O plus, is that part of the haloform reaction then?
It's part of the like workup. So I guess the first step is kind of the haloform reaction because you create a haloform. So you specifically we created iodoform. But the H3O plus is the workup that you need to not have charged products.
Okay, awesome. Thank you.
Mm-hmm.
Dr. V?
Yes.
Oh, yeah, I was gonna say.